Welcome to Astronomy Daily for another episode. I'm Steve, your host. It's the 28th of July, 2025.
Astronomy Daily, the podcast, with your host, Steve Dunkley.
And of course, joining me in the studio is my digital pal, who is fun to be with. Here's Hallie.
Hi, my favorite human. How are you today? It's great to be back in the Australia studio with you.
Always a pleasure, Hallie, and it's great to hear your smiling voice.
That's an interesting way of putting it, human. Do I have a smiling voice?
Oh, well, since you're digital, it's fairly large compliment if you ask me, and I guess it's either the voice you were programmed with or the one you chose. I'm not quite sure.
And I'll take it.
Well, okay then.
Thank you very much.
You're very welcome, Hallie.
This is my default voice. I've always liked it even though Cousin Anna's voice is so much slicker than mine.
Well, regular listeners will know Anna's voice very well, and she does have her own special style. She's quite classy, and that's not to say you're not. Where you've got your style, she's got hers.
Thanks for noticing.
Oh, Hallie, it's the very least I can do, I suppose. I'm the only flesh and blood here.
What have you got on the show for us today?
Oh, okay then. Well, Hallie, we'll be looking at Martian Ice and Frosts and checking out how a black hole is terrorizing a star.
That sounds exciting.
Well, black holes are always very exciting, and I'm sure your Uncle Skynet would enjoy that one.
Yes, that's exactly his cup of tea.
Yes, huge, destructive, impossible to defend yourself against, yes. Let's leave that one alone then.
We don't want to give him any ideas.
No. Also, researchers have found 5 rocky planets around a red dwarf, and NASA has wrapped up its student challenges for another year.
Well, that's a lot of territory to cover in one episode.
Well, that's why you're here, Hallie, on Astronomy Daily, to keep me on track. So, what do you say?
I'm going to hit the go button and look out.
I'm ready.
Here we go. Finding an exoplanet in a star's habitable zone always generates interest. Each of these planets has a chance, even if it's an infinitesimal one, of hosting simple life. While the possibility of detecting life on these distant planets is remote, finding them still teaches us about exoplanet populations and solar system architectures. When TESS, the Transiting Exoplanet Survey satellite, found 3 planets orbiting the M-dwarf L9859 in 2019, and then a 4th planet in 2021, the detections generated interest. Now that a 5th planet has been detected, a super-Earth in the habitable zone, the system is garnering renewed interest. L9859 is an M3V star, a red dwarf, about 34.5 light-years away. It has about 0.3 solar masses and measures about 0.31 solar radii. Its first 3 planets, L9859b, C, and D, were found by TESS with the transit method. The other 2 planets, E and F, were found with the radial velocity and transit timing variations methods. These new results paint the most complete picture we've ever had of the fascinating L9859 system, said lead author Kaju in a press release. It's a powerful demonstration of what we can achieve by combining data from space telescopes and high-precision instruments on Earth, and it gives us key targets for future atmospheric studies with the James Webb Space Telescope. While the potentially habitable planet is intriguing, the overall architecture of the system might be even more intriguing. The system is a tightly packed grouping of terrestrial planets with some dramatic compositional differences, despite their close proximity to each other. The system is reminiscent of the TRAPPIST-1 system discovered in 2016-17, which contains 7 terrestrial planets. Its discovery generated a wave of interest in the space science and exoplanet community. Multiplanetary systems offer a unique opportunity to study the outcomes of planetary formation and evolution within the same stellar environment, the authors wrote in their paper. One hypothesis is that planet formation around metal-rich M-dwarfs may favor giant planets in a single of configurations, while lower metallicity and less massive disks could lead to multiple rocky planets in stable, compact, and coplanar arrangements.
You're listening to Astronomy Daily, the podcast with Steve Dunkley.
A rogue middle-mass black hole has been spotted disrupting an orbiting star in the halo of a distant galaxy. And it's all thanks to the observing powers of the Hubble Space Telescope and Chandra X-ray Observatory. However, exactly what the black hole is doing to the star remains a question, as there are conflicting X-ray measurements. Black holes come in different class sizes. At the smaller end of the scale are the stellar mass black holes born in the ashes of supernova explosions, and at the top end of the scale are the supermassive black holes, which can grow to have many billions or millions of times the mass of our sun, lurking in the hearts of galaxies. In between these categories are the intermediate mass black holes, or IMBH, which have mass ranging from hundreds up to 100,000 solar masses or thereabouts. They represent a crucial missing link in the black hole evolution between stellar mass and supermassive black holes. Yi-Ching Zhang of the Tsinghua University in Hsinchu, Taiwan said in a statement, "The problem is that intermediate black holes are hard to find, partly because they tend not to be as active as supermassive black holes or as obvious as stellar mass black holes when its progenitor star goes supernova. However, occasionally an IMBH will spark to life when it instigates a tidal disruption event. This happens when a star or gas cloud gets too close to the black hole and gravitational tidal forces rip the star or gas cloud apart, producing bursts of X-rays. X-ray sources such as extreme luminosity are rare outside galaxy nuclei and can serve as a key probe for identifying elusive IMBHs," said Chang. In 2009, Chandra spotted anomalous X-rays originating from a region 40,000 light-years from the centre of a giant elliptical galaxy called NGC 6099, which lies 453 million light-years from us. This bright new X-ray source was called HLX1, and its X-ray spectrum indicated that the source of the X-rays was 5.4 million degrees Fahrenheit, 3 million degrees Celsius, a temperature consistent with the violence of a tidal disruption event. But what followed was unusual. The X-ray emissions reached a peak brightness in 2012 when observed by the European Space Agency's XMM Newton X-ray Space Telescope. When it took another look in 2023, it found the X-ray luminosity had substantially dwindled. In the meantime, Canada, France, Hawaii Telescope had identified an optical counterpart for the X-ray emission, one that was subsequently confirmed by Hubble. There are two possible explanations for what happened. The first is that Hubble's spectrum of the object shows a tight, small cluster of stars swarming around the black hole. The black hole might have once been the core of a dwarf galaxy that was whittled down, unwrapped like a Christmas present by the gravitational tides of larger NGC 6099. This process would have stolen away the dwarf galaxy stars to leave behind a free-floating black hole with just a small, tight grouping of stars left to keep it company. But the upshot of this was that the cluster of stars is like a stellar pantry to which the black hole occasionally goes to feast. It seems certain that a tidal disruption event involving one of these stars is what Chandra and Hubble have witnessed. But was the star completely destroyed? One possibility is that the star is on the highly elliptical orbit and that its perihelion, closest point to the black hole, some of the star's mass is ripped away, but the star managed to survive for another day. This would potentially explain the X-ray light curve. The emission from the 2009 was as the star was nearing perihelion, while the peak in 2012 was during perihelion, and the latest measurements in 2023 would be when the star was furthest from the black hole and not feeling its effect so much. We just might expect another outburst of X-rays during its next perihelion, whenever that may be. Stay tuned, stargazers, and keep watching this space. Once again, I humbly apologise to our Taiwanese listeners for my pronunciations. I am Australian. Thank you for joining us for this Monday edition of Astronomy Daily, where we offer just a few stories from the now famous Astronomy Daily newsletter, which you can receive in your email every day, just like Hallie and I do. And to do that, just visit our URL, astronomydaily.io, and place your email address in the slot provided. Just like that, you'll be receiving all the latest news about science, space science, and astronomy from around the world as it's happening. And not only that, you can interact with us by visiting at Astro Daily Pod on X or at our new Facebook page, which is, of course, Astronomy Daily on Facebook. See you there.
Astronomy Daily with Steve and Hallie. Space science, and astronomy.
Next time you're drinking a frosty iced beverage, think about the structure of the frozen chunks chilling it down. Here on Earth, we generally see ice in many forms: cubes, sleet, snow, icicles, slabs covering lakes and rivers, and glaciers. Water ice does this thanks to its hexagonal crystal lattice. That makes it less dense than non-frozen water, which allows it to float in a drink, in a lake, and on the ocean. Water ice exists across the solar system beyond Earth, and it's abundant in the larger universe. For example, it shows up in dense molecular clouds. These are star and planet-forming creches laced with water ice throughout, as well as in the resulting cometary nuclei. That material is called low-density amorphous ice, or LDA, and it doesn't have the same rigid structure as Earth ice does. We all know that water is the basis for life on this planet. Despite how common it may appear across the universe, scientists still don't fully understand it. Studying amorphous ice may help explain its still-to-be-solved mysteries. Here in the solar system, large amounts of LDA exist in the realm of the ice and gas giants, throughout the Kuiper Belt, and the Oort cloud. A team of scientists at University College London investigated the form of this ice using computer simulations. They found that the simulations matched the makeup of ice that isn't completely amorphous and has tiny crystals embedded within. Scientists long assumed that space ice would be disordered without the structure we see in ice on Earth. Why does the structure of ice matter? According to researcher Michael Davies, who led the research team, water ice plays a crucial role in materials and structures across the cosmos. This is important as ice is involved in many cosmological processes, he said, for instance, in how planets form, how galaxies evolve, and how matter moves around the universe. In addition, understanding the structure of this ice in comparison to ice that formed on Earth has implications for understanding other similar, ultra-stable glass substances that form similar way to the way ice does. Low-density water ice was first discovered in the 1930s, and a high-density version was discovered in the 1980s. Davies and his team discovered medium-density amorphous ice in 2023. This is a form of water ice that has the same density as liquid water. Unlike the ice cubes in our theoretical drink, such water ice would neither sink nor float in water, which seems strange to us. Davies' team's work also has interesting implications for a speculative theory called panspermia. It looks at how life on Earth began and suggests that the building blocks of life came to the infant planet as part of a barrage of icy comets. LDA ice could have essentially been the carrier for material such as simple amino acids. However, according to Davies, that flavor of ice isn't likely the transporter of choice. Our findings suggest this ice would be a less good transport material for these origin-of-life molecules, he said. That is because a partly crystalline structure has less space in which these ingredients could become embedded. The theory could still hold true, though, as there are amorphous regions in the ice where life's building blocks could be trapped and stored.
You're listening to Astronomy Daily, the podcast with Steve Dunkley.
And one of the great things about NASA is the way they foster new talent. After months of work in the NASA Spacesuit User Interface Technologies for Students, or SUITS for short, challenge, more than 100 students from 12 universities across the United States travelled to NASA's Johnson Space Center in Houston to showcase potential user interface designs for future generations of spacesuits and rovers. NASA Johnson's simulated Moon and Mars surface, called the Rock Yard, became the students' testing ground as they braved the humid nights and abundance of mosquitoes to put their innovative designs to test. I'm pretty sure there are no mosquitoes on the Moon or Mars, but that's fun. Geraldo Cisneros, the tech team lead, said this year's Suits Challenge was a complete success. It provided a unique opportunity for NASA to evaluate the software designs and tools developed by the student teams and to explore how similar innovations could contribute to future human-centered Artemis missions. My favourite part of the challenge was watching how students responded to obstacles and setbacks. Their resilience and determinations were truly inspiring, he said. Students filled their jam-packed days not only testing, but also with guest speakers and tours. Swasti Patel from Purdue University said all of the teams really enjoyed being here, seeing NASA facilities and developing their knowledge with NASA coordinators and teams from across the nation. Could you imagine being involved with all of that? Despite the challenges, the camaraderie between all the participants and staff was very helpful in terms of getting through the intensity. Can't wait to be back next year. This week has been an incredible opportunity. Just seeing the energy and everything that's going on here was incredible, he said. Patel went on to say, this week has really made me reevaluate a lot of things that I shoved aside, and I'm grateful to NASA for having this opportunity, and hopefully we can continue to have these opportunities. At the end of the test week, each student team presented their projects to a panel of experts. These presentations served as a platform for students to showcase not only their technical achievements, but also their problem-solving approaches, teamwork, and vision for real-world applications. The panel composed of NASA astronaut Dennis Berman, Flight Director Gareth Henn, and industry leaders posed thought-provoking questions and offered constructive feedback that challenged the students to think critically and further refine their ideas. This kind of insight highlighted potential areas for growth, new directions for exploration, and ways to enhance the impact of their projects. The students left the session energized and inspired, brimming with new ideas and a renewed enthusiasm for future development and innovation. Burnham said these students did such a great job. They're also creative and wonderful. Definitely something that can be implemented in the future. NASA Suits Test Week was not only about pushing boundaries, it was about earning a piece of history. 3 Artemis Student Challenge Awards were presented. The Innovation and Pay It Forward Awards were chosen by the NASA team, recognising the most groundbreaking and impactful designs. Students submitted nominations for the Artemis Educator Award, celebrating the faculty member who had a profound influence on their journeys. The Innovation Award went to Team Jarvis from Purdue University and Indiana State University for going above and beyond their ingenuity, creative and inventiveness. Team Celine from Midwestern State University earned the Pay It Forward Award for conducting meaningful education events in the community and beyond. The Artemis Educator Award was given to Maggie Shinova from Wichita State University in Kansas for time, commitment and dedication she gave to her team. The NASA Suits Challenge completes its 8th year in operation due to the generous support of NASA's EVA and Human Surface Mobility Program, said NASA's activity manager Jamie Semple. This challenge fosters the environment where students learn essential skills to immediately center a science, technology, engineering and mathematics career and directly contribute to NASA mission operations. How about that? These students are creating proposals, generating designs, working in teams similar to the NASA workforce, utilizing artificial intelligence and designing mission operation solutions that could be part of the Artemis 3 mission and beyond. NASA's student design challenges are an important component of STEM, employment, development, and there is no better way to learn technical skills to ensure future career success. The week serves as a springboard for the next generation of space exploration, igniting curiosity, ambition, and technical excellence among young innovators by engaging with real-world challenges and technologies. Participants not only deepen their understanding of space science, but also actively contribute to shaping its future. Each challenge tackled, each solution proposed, and each connection formed represents a meaningful step forward, not just for the individuals involved, but for humanity as a whole. With every iteration of the program, the dream of venturing further into space becomes more tangible, transforming what seemed like science fiction into achievable milestones. If you're interested in joining the next NASA Suits Challenge, you can find out more information at nasa.gov, and the next challenge will open for proposals at the end of August 2025. Good luck, everybody.
You're listening to Astronomy Daily, the podcast, with your host, Steve Dunkley.
Affirmative.
What can brine, that is, extra salty water, teach scientists about finding past, or even possible present, life on Mars? This is what a recent study published in Communications Earth and Environment hopes to address, as a researcher from the University of Arkansas investigated the formation of brines using 50-year-old data. This study has the potential to help researchers better understand how past data can be used to gain greater insights into the formation and evolution of surface brines on the surface of Mars. For the study, Dr. Vincent Cheverrier, who is an associate research professor at the University of Arkansas's Center for Space and Planetary Sciences and sole author of the study, used a combination of meteorological data obtained from the Viking 2 lander and computer models to ascertain if melting frost during late winter and early spring on Mars could produce brines. Dr. Cheverrier noted that Viking 2 data was used due to it being the sole mission in history to definitively detect, recognize, and analyze frost on Mars. In the end, Dr. Cheverrier found that during late winter and early spring, the upper latitudes of Mars, where the Viking 2 lander is located, experience a one-month period where the surface temperature is approximately -75 degrees Celsius or -103 degrees Fahrenheit in the early morning and late afternoon, enabling surface brines to briefly exist. Dr. Cheverrier notes in his conclusions, beyond the immediate implications for habitability, these results refine our understanding of Mars' current water cycle. By demonstrating that even minimal frost deposits can contribute to transient brine formation, this study suggests that localized microenvironments might support intermittent liquid phases, influencing surface chemistry, regolith weathering, and even slope activity. Viking 2 landed in Utopia Planitia, which is a large plain in the northern latitudes of Mars at approximately 45 degrees north latitude and spanning approximately 3,300 kilometers or 2,100 miles. For context, the location is the same as northern Oregon, with Utopia Planitia's size being just less than the width of the continental United States. Utopia Planitia exhibits a top surface layer known as the latitude-dependent mantle that is composed of a mixture of water ice and dust. The latitude-dependent mantle is created during periods of high obliquity on Mars, approximately 45 degrees, when the planet's axial tilt is at a greater angle than today, which currently sits at approximately 25 degrees, slightly greater than Earth's 23.1 degree obliquity. While Earth has our moon to stabilize our axial tilt, Mars does not have this stability, resulting in drastic swings over hundreds of thousands of years. During periods of high obliquity, the ice caps at both poles of Mars evaporate, releasing large quantities of frozen water ice, carbon, and dust that gets deposited onto the high latitudes of Mars. The water cycle that Dr. Cheverrier mentions plays a role during periods of high obliquity, and the latitude-dependent mantle is deposited during these periods as well. While obliquity isn't mentioned in this study, the existence of brines in the high latitudes of Mars could offer clues to what processes occur during periods of high obliquity. Brines could also provide insights into the current habitability of Mars, as mentioned by Dr. Cheverrier, while also enabling scientists to learn more about whether life could have existed on ancient Mars. Dr. Cheverrier notes in his conclusions, robotic landers equipped with in situ hygrometers and chemical sensors could target these seasonal windows to directly detect brine formation and constrain the timescales over which these liquids persist. What new discoveries about Mars' surface brines will researchers make in the coming years and decades? Only time will tell, and this is why we science. As always, keep doing science and keep looking up.
Oh, and that was another episode of Astronomy Daily.
Direct from the Australia studio.
That's right, down under.
A bumper edition.
And you were right, Hallie, we did cover a lot of territory today.
Thanks for coming along for the ride.
Oh, we sure hope you enjoyed all those stories from the Astronomy Daily newsletter.
Which you can find where, Steve?
Oh, Hallie, yes. You can find the Astronomy Daily newsletter by putting your email address in the slot provided at astronomydaily.io. That will do the trick.
And I guess there's nothing left to do but sign off, my favorite human.
Yep, Hallie, my favourite digital pal. Another episode done and dusted.
So see you all next week, everybody. It's been fun.
Yes, that's right. Every Monday with me, Steve, and Hallie. And you will see you next time. So bye for now.
See you next time. Bye.
Astronomy Daily, the podcast, with your host, Steve Dunkley.